Okay, so chapter 18. That one's going to be dealing with a few reactions, like 7 reactions or so. And we're only going to be focusing on the most acidic proton between carbonyl groups. Okay, so that means that RU and pKa values, they're coming back. Okay, do you guys remember how to use RU? I see one yes. Do you know how to use RU to determine which molecule is most acidic? A little bit. Okay, we're going to review today. Okay, now, but usually 18, we just like to call it the chapter with tautomers. Okay, tautomers is something similar to what you've seen before. It's a kind of isomers. So far, we know about constitutional isomers. We know about stereoisomers. These guys are going to be called structural isomers. And then let's do a differentiation. Okay, so tautomers is going to be whenever you do an intermolecular conversion between structures. So you can pretty much start guessing by the bottom portion, by those 3 molecules, that the backbone, the skeleton, is going to stay the same, but we're going to be shifting around some electrons, but we're also making new bonds. So let's just quickly write the definition. Now you have to keep in mind that this is not the same as resonance, for example. What was the definition of resonance?
Oh, well, resonance involves like moving the double bonds.
Moving the double bonds, exactly. We're just moving electrons. Remember that we're not bringing any single bonds or anything like that. Mm-hmm. So we can just say contributors of the same structure. That shift electrons. Okay. Yes, intermolecular conversion between structures. Okay, now we're gonna see how the tautomers are created. Now we have 3 main forms for our tautomers. We have something called the keto form, the enolate, and the enol. Okay, let's start with the simple one. So first of all, tautomers are gonna be especially only with your carbonyl groups. In more advanced class, you might see them with other functional groups, but for this one, we're just gonna focus on the carbonyl, specifically ketones and aldehydes. So let's just start drawing the backbone of a ketone in here. Okay, that's my ketone. And remember, I'm gonna use any sort of base in here. It can be NaOH. I just added. No, this one we know that it's a ketone. So this guy is just called the keto form. Okay. If it looks like a ketone, keto form. Simple as that. Now, what were the alpha positions? Where can I find them? Okay, so we have 2 alpha positions and we have hydrogens on both sides. But remember, the whole goal is always to create something really, really stable. So we're always going to tend to pick the most stable side, the more substituted side. So we're just going to be focusing on the right. But, okay, your alpha hydrogens are going to be considered relatively acidic. So that means that a base is going to be very attracted to them. So the base is going to be taking away that hydrogen. The electrons between bonds of carbon and hydrogen is going to shift in between the carbonyl and the alpha carbon. And then to not break the octet, we know that we have to kick up the electrons towards the oxygen. So we're forming this little guy in here. And those are still my alpha positions. Now, once we have the pretty much the deprotonated version of the molecule in the alpha positions, this guy is going to be called your enolate form. Your enolate is always going to have some sort of negative charge, especially in the oxygen. Now, the other one is going to come with the conjugate acid of the base. So once we use the base, we know that that base took away that hydrogen. So we're creating, let's just write HB in this case. Okay, that's my acid. So that oxygen minus from the enolate is going to take that hydrogen. And of course, we break the bond between hydrogen and base. So we end up with this guy. Now, because we have an alcohol group, this guy is going to be called your enol form. Oh, well, remember that's an alcohol group. So it's very simple in a way. Okay, now, main takeaway is that your base catalyst creates both the enolate and the enol form. So far, questions? We're good?
Yeah.
It makes sense? Okay. Now, let's see what happens if we use an acid instead. So let's just use H3 plus. Why not? Okay, and we're going to be starting with a ketone as well, which we know is just the keto form. I have my alpha positions. Now, in chapter 16 and 17, what did acids do to the reaction? How did they affect them? It makes the electrophile more electrophilic. So that oxygen in the carbonyl is actually going to get protonated. So it becomes more electrophilic. And then we still have our alpha positions in here. Now, this one, it's not the enolate form. So keep that in mind. Not yet, because we still have that carbonyl. So water now is going to do the same thing that we saw with the base catalyst in the very first step. So our oxygen in water is going to be abstracting that hydrogen, the acidic alpha hydrogen. We shift the electrons to make the doublet, and then we kick up the electrons towards the oxygen. So now we end up with the enol form. And this guy is just your enol form. Okay, so far questions. Make sense? You're getting enol forms for both, yes, but only the enolate with the base.
Yeah,
So yeah, keep that in mind. No. Again, that's the main part. Base creates both the enolate and the enol form, but acids, those guys only enol. Okay. So far, any questions? Pretty simple. We can follow the mechanism. It's very similar to what we've seen over and over again at this point. And let me know when you guys are ready. I see that some of you are still taking notes. Mm, it would be good that you know the mechanisms for chapter 18 in general. Yes.
These, like, within the-
No, usually whenever we're talking about tautomers, he likes to ask, given X form of keto form, which is a possible enolate form if we use a base as a catalyst or things like that. Or what are the tautomers that are formed if we use an acid? We know that if it's an acid, it's only the enol form. If it's a base, we form both. So with tautomers, you're not really going to see them in the reactions themselves. We might see how they play a role in them, but not quite like this. Okay. Let's go through the next simple concept in here, which is going to be racemization. That one sounds very familiar, actually. Do you remember that from Orgo 1? Racemic mixture, exactly. What does that mean? What was a racemic mixture? Which one? Exactly, yes. So racemic mixture, it was just equal amounts of both R and S configurations. Okay, no. In this case, remember, chapter 18 main focus is alpha hydrogens. So for racemization, of course, some sort of chiral center is going to be involved. So let's just write. Whenever they're asking you for which molecule can undergo racemization, you're looking for a chiral center present in your alpha carbon. And alpha carbon that has an alpha proton as well. So again, we're just focusing on our alpha carbons. So this is alpha, alpha. Whoops. Okay. So which molecule has a chiral center present in your alpha position that also has a proton? C. Mm-hmm. C is the only one, remember. How do we find a chiral center?
Or
4 different groups, exactly. That's it.
which only C has.
Mm-hmm.
A has like the gauge. And B and D, like, they're basically.
Yeah, pretty much, yes. Okay, questions. It's very simple. We're kind of just playing around with the concepts that we learned before. Okay, we're good. Yes. And specifically in the alpha position. And then let's go back to acidity. Okay. Let's start simple with those 4 molecules. Which one do we think is going to be the most acidic and why? The acid anhydride, that's from chapter 17. Yes, that's one of them. Is it C? Is C the acid anhydride? It looks similar to it, but what am I missing?
Oh, the O in the middle.
The oxygen in the middle. So not quite the same. Okay, if we're not given pK values, we're just going to start using either cardio or aria. They're the same exact thing. Okay, so we know that it just stands for atom, resonance, inductive effects, and then orbital. Okay, so remember, for ARIA, you have to go through each of the specs individually. Once you're done with one level, you can move on to the next one. So first, let's start with the atom. So in this case, those are going to be our acidic protons. Whoops, over there. Okay, which one is connected to an electronegative atom? Directly connected to it. A is the only one that's connected to that oxygen directly. That one is the most acidic. Yes. So let's just label it as 1. Okay, which one is the least acidic? B, yeah, it's just pure carbon chains. There's not that much stuff going on in there. This guy is 4. Now we're between 2 carbonyls versus 1. Which one is going to be more acidic and why?
Honestly, probably use second carbonyl, but 2 carbonyls is more acidic.
Was there an agree? So yes.
But it also
Yeah, it also does resonance because once that hydrogen goes away, we're left with a little negative charge that we can stabilize throughout that portion. So yeah, this one, it's going to be more acidic than option D. Okay, so acidity is not too bad. It's not too bad. What was the trend with pK values? How do we know something is more acidic based on their pK values? The lower the pK. Don't confuse them. Please don't confuse them. Okay, let's look at this little bit molecule in here. You have a few options in here. Which one is going to be the most acidic hydrogen and why? Which ones could you start discarding right away?
is
We're just going to discard G, just pure carbons. What else? D as well and A as well, yeah. They're not that exposed to anything very electronegative. E is also far away. What else? F as well, it's similar to A. Why B? Because that's the phenyl group, exactly. That phenyl group is going to provide more resonance.
Oh, it's a B.
That's why it's this guy.
Because these only test like
Yes, it's similar to what, whoops. It's similar to what we saw over here in molecule C.
yeah, these are structures, but one that has like
Okay. Questions so far? It's pretty simple.
that's bad.
It's not too bad. Exactly. It's not too bad. Okay, and now let's get started with the reactions. And at this rate, I think we're gonna be pretty good. 2, 2, 3, 4. I think we're gonna be able to go through the first 4 reactions of the chapter. Hopefully. But either way, the very first one is one that sounds the exact same as previous reactions, halogenation. We've seen that one so many times, back in Orgo 1, Orgo 2. So how are we gonna differentiate them? How do you know that you're doing a certain type of halogenation versus another? If they have the same exact name.
That's the reason phase.
That's the difference between hydrohalogenation and halogenation. But we saw halogenation, for example, back in chapter 15. Okay. And now we see it again in chapter 18. They have pretty much the same exact reagents. They both have Br2. What about the bottom portion, the solvent? Is it the same? What was the solvent for chapter 15? A Lewis acid, specifically. A Lewis acid. So remember, they might have the same name of the reactions, but the main components that are working on them, they're going to be different. Okay, so again, do your list of reagents. They sound the same exact, but again, they're different based on what you're presented with. Either way. Let's start with our base catalyst. And then we're going to do the acid catalyst reaction. Okay, now you have to keep in mind that the following reactions are going to happen in both acids or bases. Okay, and it's mostly just going to be with ketones, and there's a few with esters. Okay, but for the first ones, we're just going to be working with ketones or aldehydes. Okay, now remember, the main focus of the chapter is the alpha positions. Why? Because they're very acidic. And then remember, we're always trying to create the most stable molecule. So you're going to focus specifically on the alpha position that's most substituted. Okay, so we saw this step before.
Yeah.
What's going to happen?
Well, the negative charge will go to hydrogen,
Mm-hmm.
and that bond will go up to the double bond. And then the bond that will go to oxygen will go up to the negative charge.
Beautiful, exactly. That's something that we've seen so many times at this point. So we're creating O minus in here. Okay, what's the name of that one?
That's an analyte.
Beautiful, that's your analyte. Okay, I have my analyte. I use my base, but I still have
There's still the
the halogens. What do you think is going to happen? What's going to be acting as the nucleophile and what's going to be acting as the electrophile?
Well, I think I did that the negative charge would be drawn to the halogen, probably, but I'm not sure.
So that's a pretty good guess. We know that negative positives, they attract each other. What else? How do we know?
One of the acids supposed to be positive, that will attach to the oxygen.
Not quite.
That's something else.
So yes, that was for chapter 15. Because remember, the whole point of Lewis acids was to make the electrophile more electrophilic. In chapter 15, we needed that because we didn't have the active electrophiles. So we know that Br2, for any pure halogens, those guys are going to consider your electrophiles. They're the ones getting attacked. Benzene, we know that was our nucleophile because that was doing the attack, and it's because it's also very electron dense. In this case, a double bond is going to be very electron dense, so that's going to be triggering the reaction. Now, specifically, for chapter 18, we're trying to preserve the carbonyl groups as much as possible. So something that we've seen before, we're going to be reforming the double bond, and then our electron dense double bond is going to be attacking our halogen. So we're back to the ketone, but now we have a bromine in the alpha position. Now, for chapter 15, we were talking about polysubstitution a little bit with NH2, right? That was your really strong activator. What did polysubstitution mean? How do we know we're doing polysubstitution? What's going to happen? That's undesired polysubstitution. Okay, so first of all, we know that polysubstitution is promoted by NH2 and amine. Can Friedel-Crafts reactions happen with amines? They cannot.
No, no.
So they're going to be happening with the rest of the 3 reactions left over in chapter 15. Now, poly means many. Substitution, you're just substituting as much as possible.
Right.
So we're going to apply something very similar in here. Now, this is only going to happen whenever you're doing your halogenation in bases specifically, okay? Because the base is so strong, it's going to be promoting the reaction to go through once more, so you can do a poly substitution of all of your alpha hydrogens, specifically just on the more substituted portion, which is on the right. So we're going to be with this little guy with 2 bromines in the alpha position. And again, this only happens with bases.
Okay, got it, okay. Because I'm wondering, I just, I know it's that one bromine thought. So, they say that the bases that other bromine gets attached.
Okay, now. Questions so far with the mechanism? Pretty similar to what we've seen before. It's not too crazy. Okay, now. In this case, we know that water can be both acids or bases. In this case specifically, water is going to be acting as your acid. What's going to happen in the very first step? What's going to attack the bromines? What was the role of acids? The oxygen is going to be attacking those guys, so we can make it more electrophilic. So we have an oxygen with a positive charge, a little hydrogen, and again, we're focusing on alpha positions. Okay. Now, from that step,
Yeah,
I have OH minus, exactly. So what do we think is going to happen in here?
it's just a base catalyst reaction, so. Yeah, so negative goes to the hydrogen, double bond, and now we have an NO.
Now we're creating the enol form specifically. So we have little guy, OH, and we know this one is just called your enol form. We still have the bromines left. So what's going to happen? What happened in the previous reaction that we just did?
It's a reaction. Let the electrons one back to the double bond, and then the double bond, the other electron is attack the bromine.
So in this case, even though we have an alcohol group this time and not oxygen minus, we still have to reform the double bond.
The same.
Same exact thing. So reform the double bond, then your electron dense double bond attacks bromine. So we end up. Okay, we are back to a positively charged oxygen. And now we have our dear bromine in the alpha position. Now remember, we want to create something that's really stable, so I'm just gonna deprotonate that guy. So it's not as reactive. So let's just say that it was basic and be water, anything really. So we can just neutralize this guy. And that's it. So they are pretty similar, but again, depending on whether you use a base or an acid, you're gonna get different tautomers. Now, what would be a shortcut for this reaction? Exactly, simple as that. Just replace alpha hydrogen for whatever halogen you were presented with. So yeah, you don't have to do the full mechanism to get the gist of it. As long as you know that shortcut, you should be good. And as long as you know the difference between bases and acids, remember bases promote polysubstitution, okay? So in this case, actually, let's do our little chart. of bases. And then acids. Okay, now, whenever we use an acid as a catalyst, the very first step, what happens in there?
The negative oxygen attacks the acid first.
So the oxygen attacks the acid, yes. So we protonate that oxygen, protonate oxygen and carbonyl. Okay, now what kind of tautomers do acids create? What's the name? It's the enol form, exactly.
Oh, right, okay. I'm not sure you asked.
So yeah,
But yeah,
don't worry.
It creates the
What about bases? What do bases create? Which kind of form?
It creates the
Enolate, beautiful. And then let's just make a quick note on the polysubstitution.
Yeah, and
So,
you can have like both.
So pretty much each halogenation promotes another one, another halogenation. Okay. Questions on halogenation? Pretty simple. We have a shortcut for it, so don't get overwhelmed with the mechanism. Again, main portion is just the conceptual stuff that's over here in our little chart at the bottom. Okay. Okay, ready for the next reaction, which is your haloform reaction. And it actually sounds very similar to a reaction back in Orgo 1. Okay, now. Before I show you the mechanism, let's talk about certain requirements for this reaction. So for this one, you're gonna need a special type of ketones, okay? The ketone, your starting ketone, has to have one methyl group on one side. Why? Because we want 3 available alpha hydrogens, okay? So let's just start writing that. Methyl with 3 alpha hydrogens and no alpha hydrogens on the other side. That's why the benzene is. What else could I put in there instead of the benzene group? 3 other methyl groups. And what about an aldehyde? Is that hydrogen considered alpha? No, exactly. It's not considered alpha. Okay, so that's our requirement, first of all. Okay, now the other requirement for this reaction is going to be an excess of the base. Okay, it can be any basis, but it has to be in excess. Okay, so again, we're just going to be looking at our alpha positions. Okay, we have our alpha positions, we know that. We have our 3 hydrogens available in here. Okay, if we have a base, we've seen this before.
Yeah.
Very first step, what happens?
The OH attacks the more alpha.
In this case, yeah, it is actually only going to attack one side because we only have one possible attack.
Yeah.
So yeah, we take it away, we create our double bond, we kick up the electron so we don't break the pore octet.
That part's enough.
That part is very easy. It's pretty much, they all have some sort of step in common. You're going to see the same.
Like the other hydrogen.
Okay, so we have an oxygen minus, we have a double bond, and I have my 2 hydrogens from the initial methyl group. Okay. Now that guy, what's the name? What's the name of the tautomer?
This is it's still enolate.
This guy is your enolate.
Okay.
Okay.
It has like the base like O and double bond next to it.
That's how you know you have an enolate. So again, please remember how to identify an enolate and an enol. You might get a few questions on that. Okay, so we have those guys, and I still have my dear halogens in here. So we've seen this step before.
Yeah.
Oxygen is gonna drop its electrons down. Electrons in the solvent attacks our halogens. So we have our ketone again. That's connected to our bromine, and we still have the two hydrogens from the initial method group. Okay. So far I'm basically just doing the same thing as a halogenation. So far it looks the same exact thing, but remember we have excess. So of course this reaction is not going to be as easy as that. We're going to keep going. So in this case, our dear base, OH minus, comes once again. Again, remember, they are attracted to very acidic protons. We attack it, we create a double bond, and we move up the electron so we don't break the octet. So we have this little guy in here. Oxygen minus, double bond. I have my bromine and the leftover hydrogen. And again, what's that form called? It's still an enolate, exactly. Exactly. You're gonna repeat the same process for every single alpha hydrogen. So let's let's bring back our dear bromines. We bring back down electrons. We attack. And then we're back. Exactly. So we have the first one from the very first reaction. We have the one that we just added. And then the little leftover hydrogen. But again, excess of the base, we're going to repeat the same exact process. Do you guys? Yeah. Do you guys want to show you the repetitive process again? Up to you. It's completely okay.
So, but I think the errors of that would basically have an enolate with gray bromine, pretty much. That's basically it. All this thing.
Not quite. Not as simple as that. Not as simple as that. Okay. So let's see. Let's just repeat the same process of it. Do I have more space? Yes, I do. Okay. Okay, so I have my two bromines in here. So we're going to repeat this step once more. So we know that at the end, we have our benzene. We have, oops. Let me just keep this the same. Bless you. And then the third bromine in here. Okay, now. Remember, we still have excess of the base. Now, the base, we don't have any more acidic alpha hydrogens. But this base can also act as a nucleophile. So remember that whenever we have a carbonyl, that dipole moment is creating a delta positive on the carbon, making it electrophilic. So this guy is going to get connected to the carbonyl. We kick up the electrons, of course, so we don't break the Bohr octet. So we end up with this intermediate so far. We have oxygen minus. We have the nucleophile connected to it. And then all of the bromines that we added. Okay. Now, this portion is going to look somewhat similar to chapter 17. For chapter 17, remember, we always kick out some sort of leaving group and we end up reforming the carbonyl group. That was the whole gist of 17. Now, in this case, I want to reform my carbonyl, so we go back down. And now, what's going to be my leaving group, the OH or my bromines? It's going to be the bromines. That's just going to be your halo form. Therefore, that's the name of the reaction. So we kick all of this out. And then we're going to end up with what kind of functional group? What's the name of it? What's the name of that guy? Which one? Carboxylic acid, exactly. Simple as that. It's a carboxylic acid. And then technically, yes, you're going to have your byproduct, which is going to be the halo form, which is just a little carbon with 3 bromines. Again.
So basically with the excess, that's the reaction over and over.
We repeat the reaction over and over again. Yes.
But the last step is kind of
The last portion, that's the main thing. So what's the shortcut for this reaction? What do we notice?
well, we can skip the whole excess portion.
We can skip all of the excess portion. Exactly. We're not going to waste our time with all of the mechanism.
Yeah, that'll take a while.
Mm-hmm.
Like that, the part really important, but it's like the part after the excess. So,
Mm-hmm.
so yeah, we just throw that before the excess.
Exactly. So pretty much you're going from a ketone to a carboxylic acid. That's the main portion. Now, remember the requirements, okay, for this reaction, the ones in purple. Those are important. That's how you know you're doing this reaction. Because remember, if you just look at the reagents, it looks pretty much the same as a normal halogenation.
But
So again, be careful in all of the components combined, okay? So not too bad. It's just, yeah, it's just repetitive. You don't really have to do all of that on the exam. You don't have time. Please don't do the full mechanism.
yeah,
Please use your time wisely. Yes. He's just going to be asking for products. Exactly. Mm-hmm. Tautomers are fun because you might see them, how they play a role in our biological systems once you take biochem, but they're just going to mention it very briefly. They're not going to ask you, show me the mechanism. No. They're just going to talk about it and different tautomers forms. That's it. Simple as that. So it's been an hour, guys. I thought we were going to get through more reactions, but still, we did pretty good. And actually, the mechanisms that we just did, they're going to be pretty much the same for the next 3 reactions. So you can give it a try on your own. Watch the recording that he posted, so you're all up to date. And then, yeah, I'll see you guys next week. So enjoy your holidays. Happy Thanksgiving, guys. There you go, Abby.